G'day IB students. Ms. Reish has asked me to come along and give you a little bit of a chat about the maths and the statistics and what you're going to need when you're writing up your IAs and that sort of thing. So what I've got in front of you there, you should hopefully see the mathematical requirements for diploma students in sport, exercise and health science. I'm going to run through a bunch of different things about this, give you a few tips. It's really hard to be able to tell you exactly what to do without seeing your design, but hopefully from this you'll get a feel for what they're going to be looking for, what sorts of things you should be trying to include when doing your stats. So let's go ahead, see where we get, and then hopefully I'll drop into a Zoom sometime and you guys can have a chat with me more, and hopefully I'll be able to help you. So let's have a look at the mathematical requirements, the basic functions. I'm going to tick that off. You guys can do that already. Can you carry out simple calculations involving means, decimals, fraction, percentages, ratio, approximations, reciprocals, and scaling? Yes. We've done standard notation, scientific notation before. Direct and inverse proportion. Direct proportion, where you increase one thing by a factor, you increase the other thing by a factor. Inverse proportion, if you multiply one by a factor, the other one gets divided by that same factor, so their product is always the same. You can ask your maths teacher about that, but you should be all over that by now. A few things worth noting here that we might need to think about. So represent and interpret frequency data in the form of bar charts, column graphs, histograms, and interpret pie charts. So it's interpret and represent. So you've got to be able to produce these things. There are lots of tutorials available on YouTube or online. You probably know how to do most of them already. Histogram, remember that's for continuous data. Column graph for categorical data where they're separate or discrete. Pie charts, so to get the angle, it's just the proportions. That's showing proportionality. I think you're probably mostly familiar with those. If you've got some questions about those, happy to have them, but I think you'll be all right with those. Determine the mode and median of a set of data. Calculate and analyze standard deviation. And you need to understand what the advantages and disadvantages of these different things are. So for instance, back here where we're talking about the mode, a median, and of course you sometimes talk about the mean as well. We need to know what's the most suitable measure of center for each of the different sorts of data we have and why we might use one over the other. So a mode, obviously, if we've got categorical data where you have to choose from one of a number of categories, that's the only one we've got available to you if we've got non-numeric data. So for instance, if we wanted to know what's the most popular flavored soft drink that they sell on Red Food Days in outside the chapel, well, we could do an analysis, and the mode, the one which sold the most, that would be one which we would say is the most popular. So it's the measure of center, if you like. A median is a great measure when we have data that isn't normally distributed. So normally distributed data, hopefully you've done that in maths by now, but that's where you get like your nice bell-shaped curve, where things are, we have a few down one end that are extremely big, a few down the other end that are extremely small, or the other way around. I don't know how that's coming out for you. And they seem to be approximately bell-shaped, spread out between those, with most of them occurring around the mean. If we have that sort of distribution, a mean is really good. A median is also okay. But when you have a skewed distribution, so when there are a few extreme values, either extremely large or extremely small, or even just one really far outlier, they tend to affect the mean and make it less representative of the middle. And in that case, using the median, it's not going to be affected by an outlier because it's still just the one in the middle, so the outliers aren't really affecting the calculation for that. So in that sense, a median may be a better measure of center. Same with standard deviation versus, say, your range or your interquartile range. They're all measures of spread. The standard deviation is great for normally distributed data. It's very powerful. If we have normally distributed data, using a mean and standard deviation, we can work out probabilities and proportions very easily and quite powerfully. When we don't have normally distributed data, it's not so effective, so then we tend to be using a median and then perhaps the interquartile range or the range. Again, the advantage of an interquartile range over the whole range is the interquartile range is not going to be affected by outliers. So as a measure of spread, it's probably more representative. The range, because it could include possible outliers, that's going to make a big difference. So if we were all in the classroom together and we, measured the weight of everyone in the room and tried to find an average, because I'm significantly heavier than anyone else in the room, I'd be dragging the mean and make the average that we got using the mean probably higher than it really is. the median would be a much better representative value for the weight of people in the room. Same if we were doing the variation between people. If we took my weight and the lightest person in the room and found the difference in that, that's a huge range, you know. But really, is there that much variation in the room? Not really. There's just this one extreme value, and the others are all fairly close together. So probably we're better off using an interquartile range or something that doesn't include those outliers. And so I've got a little note there about the strengths and weaknesses. I'll send you this page from my OneNote so you'll be able to see it all there. There it is. I couldn't see that little thing. Drag it along. Oh, it doesn't want to drag along a little bit. Maybe it'll let me do it with my hand. Oh, it's misbehaving. Anyway, so the strengths of a standard deviation, it uses every piece of data. That's a good thing. And it's reliable when we've got that bell shape, that normally distributed data. Weaknesses, it's going to be affected by outliers. So it's really important, whatever statistical test you're choosing, you just make a comment about why you're choosing that test. If you're using a measurement to represent the center, why you think that's the one to use. Is it because it's not affected by outliers, or are you choosing the mean because it is normally distributed, so you'd expect that to be the case? They're the sorts of things that will separate you from someone who just calculates it. Just a little statement about why it's the correct one to use would be really useful. Select statistical tests appropriate for the analysis of particular data and interpret results. So this is probably one of the harder points. How do I know which test to select? So move my head out of the way there. If we have a look over here, there are hundreds of flowcharts like these for commonly used statistical tests. Usually, so the parametric assumptions that they're talking about, because I think, well, this one mentions it, this one doesn't. But am I using independent or unbiased samples? Is my data normally distributed or not? Are the variance is expected to be equal or not? We can talk a little bit more about that. Most of you are probably heading down, yes, I'm measuring some sort of continuous data, something that you measure, and yes, you'll probably have an independent variable, maybe not. Or are you measuring differences between different conditions? If you're not doing that one, you're measuring differences between different conditions. So which tests can you go with there? And there's a few tests you can do depending on the conditions. And again, we can look down each path. Probably we're going to come out with a lot of Wilcoxon or ttest, depending on whether or not you can expect your data to be normally distributed or not. It may be that we're coming out with a chi-square or something else, but again, that will depend. You can follow through the flowchart. So if you're doing something that you measure, it's continuous data. Do you have reason to expect that this population that you're looking at is normally distributed? If you do, if it's widely known that, like, you're looking at, I don't know, reaction times of people, that's probably expected to be normally distributed. You could expect to use this section here. If you can't be sure or confident that it's normally distributed, there's not previous studies showing that you expect, the population to be normally distributed, or you just want to be more conservative, you may say, well, I can't guarantee that it's normally distributed, so I'm going to assume that maybe it's a skewed distribution of data and go from there. It's up to you to really think about that and justify that. I don't think anyone will really mind which one you choose, as long as you've made a comment and justified it. They're not going to go and research your topic and check exactly what it is. They just want to know that you've thought about it and you've made a decision because of that. Oh, now it's scrolled across. How helpful. Plot and interpret graphs with suitable scales and axes. So, yeah, people just, in IAs especially, don't forget to label axes. Make sure your scale is reasonable to show the difference between things. We don't want to have misleading graphs where you cut off a lot of the y-axis and then you're just showing, a 0.5 difference, but it looks like something's 5 times as big as the other one because of the scale you're using. Make sure you're not artificially exaggerating any differences there. Plot and interpret scattergrams. So again, Excel's really easy for that. You can also do it on your calculators. Scattergrams, x-coordinate, y-coordinate, whatever they are. And then establish a correlation. So there are lots of tutorials on how to do that in Excel. Most of your class, your year level people are going to know how to do that on Excel and on the calculator. So that should be fairly straightforward. Appreciate the existence of a correlation does not establish a causal relationship. And that's really important. There are great examples. I can't type and talk at the same, well I can, but just not very well. I'm going to show you here examples of things that are correlated that, where's my favorite website? It's one of them. Spurious correlations. This is a great website. So there is a strong correlation between US spending on science, space and technology and suicides by hanging, strangulation and suffocation. Now, would we expect that one of these is causing the other one? It's not very likely, is it? Number of people who drowned by falling into a pool and films Nicolas Cage appeared in. So a correlation at 66%, not as strong as the 99.8 that we had between spending on science, space and technology and hangings, but still that's a fairly solid correlation. Are people drowning causing Nick Cage to go and make more movies? Or are his movies causing people to drown by falling into a pool? Who would know? Per capita cheese consumption and the number of people who died by becoming tangled in their bed sheets. Is there something sinister in cheese that we don't know about? How scary is that for the number of deaths? People dying, becoming tangled in their bed sheets. That's a little bit scary to me. But look, a super high correlation, but again, not necessarily causal in that relationship. So let's not go down that path. You want to be careful when you're wording your answers. If you find a strong correlation, you can say it lends support to the fact that two may be related, and with further investigation, it may be that there is some causal relationship, but you're backing away from saying that at the moment. You're just saying that, yep, there's a strong correlation there, and that's worthy of further investigation into a possible causal relationship. You can't just conclude, therefore, this definitely caused that to happen. That's what we're trying to avoid there. And you want to be careful with your wording when you're writing it up. Usually what happens is, when you're writing it up the day before and you've forgotten all about that, you just go for this, therefore proves that. And you go, no, it doesn't. Doesn't prove that one causes the other. So make sure you do your draft early enough that you've got time to think about those sorts of things, and just don't make those mistakes. Recognize the relationships between length, surface area, and volume. One-dimensional, two-dimensional, three-dimensional. I'm sure you're aware of those, and scale factor calculations accordingly. I've got a little note over here about when you're sketching graphs with error bars. So one of the things when we look into topic 6 in particular, measure and evaluation of human performance, outline that error bars are a graphical representation of the variability of data. So when you're collecting measurements, there's some variation in there. There's some inaccuracies that are involved. It doesn't need to be as involved as when you're doing your calculations in your sciences, and you're doing your error calculations, and understand they do them differently in physics from chemistry, from biology. What you need to do for this, well, if you want to know about how to use the standard error of a mean, there's a good website that will take you through how to do that and how to get the error bars in Excel. So that would probably be what I would consider. Notes here, only the standard deviation needs to be considered. Here is so what you need to talk about is, if you've produced a graph with these on it, you need to mention them. So it's not very good to have, and here's what I was talking about. That's what that diagram is. Where I was talking about exaggerating differences. Here's one column where it's 18, 18.5, and 19. If I show the axes, the y-axis in particular there, in its full length, there's not a great variation between those, especially when you're including the error bars. If you concertina your axis and try and show it and, start at 18 and go to 19, well, now there looks like great variation. This one's, double, 2.5 times as much as the first one. It's exaggerating the differences between them. You don't want to exaggerate those differences. That's what I was talking about previously. And that's an example of the error bars. If you want to learn how to do that website there. Whenever you're producing a graph, though, you need to talk about it. So one of the funny things that happens is a lot of people will put a graph in there and think, oh, that explains it all. You need to refer to it and make it clear what you're explaining. So one, make sure you label it appropriately, give it a title, and refer to it, table 3, graph 4, whatever it is. But then say, this is the error diagram. Here's what it means. There's some variation. However, this is an acceptable amount of variation, so that's okay. I'm going to have to pause and take that phone call. I'll be back in a second. There you go, back again. Not that it took very long for you. My wife telling me that maybe you guys will be back at school sooner rather than later, possibly next week, so that'll be good for you guys. So we were talking about here, when you've made a diagram, whatever it is, whatever the diagram is, if it's the error bars or if it's something, make sure you talk about it, refer to it, say why it's important. So here is what it is. This is what it means. These are the implications for the validity of our conclusions. There's only a small error, so our conclusions based on this are probably more solid. There's quite a large variation here, so therefore there's, some question over how strong I can be in terms of making any conclusions based on this data. Something along those lines, talking about whether or not the conclusions you make are more or less likely to be valid based on the error involved in those comments. There it is. Mean and standard deviation. You'll find that there are two different standard deviations. You've probably come across that in maths. In this course, you are using a sample standard deviation, and you're using, the reason I use the sample one and it's divided by n-1 instead of n is because you're trying to use a sample to make predictions about a larger population. When you are doing that, there is always going to be greater variation in a whole population than there is in a small sample. So to artificially increase that, and there's great mathematical arguments why this is the case, but they're super complicated and that's not really important. Know that you're going to be using this sigma n-1. Sometimes it's written as an s with a lowercase x instead of the sigma x. It's the one, basically, to calculate both. It's the one that's slightly larger than the other one when you look at the number that comes out. Because when you're trying to estimate, the reason you use a sample is because it's too hard to collect data from everyone, which would be a census, so you do a little sample, but you're trying to make predictions about a bigger population. So when we do a mean, the mean of your sample is likely to be close to the mean of the population, but definitely the variation in a smaller group will be less than the absolute variation in a large group. So that's why there's a different calculation when you're doing the standard deviation from a sample to estimate the population. A better way of describing it, rather than population standard deviation and sample standard deviation, because it's always the same calculation, is it's an unbiased estimate of the population standard deviation based on the sample. No D in the word based there. Oh, purple D, that'll do. So you should specify that and not the population one. So just make sure you're clear on that. And rather than calling it, as I said, rather than calling it sample standard deviation, it's the unbiased estimate of the population standard deviation based on a sample. Yes, I'm still at school, if you can hear that bell. Students will not be expected to know the formulas for calculating these statistics. You'll be pleased to know, but you should be able to do them on your calculator. Also, it says here, AIM 7 should be taught how to calculate standard deviation using a spreadsheet or a computer program. You probably already know how to do that. If not, that will take you through how to do a bunch of the calculations there. It's just a little YouTube clip. That guy's pretty good, organic chemistry tutor, so you can check that out if you want to. Again, there's just a difference. So sometimes SX and sigma X or sigma n-1. So sigma n-1 or SX, they're the ones you're looking for. State the statistic standard deviation that is used to summarize the spread of values around the mean, and that within a normal distribution, approximately 68% and 95% of the values fall within plus or minus 1 and 2 standard deviations respectively. You'll hear this referred to as the 68, 95, 99.7 rule. It's approximate. It's not exactly 68, 68.27, 94, 95.45, so really 95.5. And then for some reason they specify the 0.7 in the 99.7 rule. Interesting. What do we know about normally distributed data? Yes, it's got that bell-shaped curve. It's approximately bell-shaped, so it's symmetrical. 2, the mean, the median, and the mode should all be roughly equal. So even with binomially distributed data, so you can see I've got discrete data there, hence the reason I'm using histograms, not scatterplot or this sort of continuous graph. Either way, you can still get the bell-shaped curve coming out of normally distributed data. Therefore, we should be able to make this assumption. So if you want to check roughly whether your data is normally distributed, we'll see what percentage of the data lies within one standard deviation of the mean. Is it 68%? Is it 95 within 2 standard deviations of the mean? Is it almost everything, probably everything in a smaller sample, within 3 standard deviations of the mean? Chances are it will be, and you'll be able to confirm that. Whether or not you actually need to confirm that in your IA, probably not, but it's something that you should still be aware of when it comes to exams or things like that. Explain how it's useful for comparing means and the spread of data between 2 or more samples. So small standard deviation, smaller variation, large standard deviation, greater variation. So it depends on what you're looking for as to what might be a better situation. If you're looking for consistency of performance from athletes, for instance, maybe you want to get that standard deviation smaller and have a high average. Whereas if you have a high average but more spread out data, well, then you've got less consistent performance, but you have some performing at a higher standard, but also some in that group performing at a lower standard than the other group, which had a smaller standard deviation, so therefore less spread out. What do they look like? So this is what I'm sort of talking about there. Here I have a group with a small standard deviation and a mean of whatever that mean is there. This could be the same sort of group with the same mean, but more spread out. The area under the curve is still 1, so that the proportion of people is still equal, but you can see there, so we'll have some people in this red group performing at a higher standard, some at a lower standard, but the consistency of performance isn't as high. Whereas in the purple group, the consistency, there's little variation between them. Most of them are performing at a similar standard. You don't always have control over that, but that's something that may be worth commenting on, and that's just what they're talking about in that little bit there. Outline the meaning of the coefficient of variation, and so a coefficient of variation, it's like a correlation coefficient, but it's the R² value, so correlation coefficient's usually only for linear data. This is for all data. Coefficient of variation is a ratio of the standard deviation to the mean expressed as a percentage. Ooh, what does that mean? This gives you a better outline here of exactly what it means. Basically, it's a statement or a number estimating the proportion of variation in the dependent variable caused by variation in the independent variable. And so you don't need to know this calculation at all, but reading through that should probably help you a little bit. Basically, the closer it is to 1, the closer the variables are in terms of the predictive ability of one from the other. So that's what they mean by the standard deviation to the mean as a percentage. Have a read through that. You won't be asked to quiz on it. They won't quiz you on it. They won't ask for a specific definition, but you do need to understand a little bit what it's talking about. And what it's really talking about is it's the percentage of variation in the dependent variable that is caused by variation in the independent variable. Deduce the significance of the difference between two data sets using calculated values for t and the appropriate table. So usually we're going to use t-tests. For the t-test to be applied, ideally the data should have a normal distribution. That's what we were talking about when we're looking over here. Normally distributed data, that's when we're ending up with the t-tests. Okay, and in this group here, we're going type of question. Where does the t-test pop up on that one? Oh, they don't even have it on that one because that's only looking at, oh no, continuous data. Do you have a true independent variable? Yes. Or no. There you go. Maybe I shouldn't have shared that one with you because they want you to... Oh yeah, there it is. There it is down there. How many treatment groups? So the parametric assumptions. Are they independent samples or unbiased samples? Is the data normally distributed? That's when we're ending up with the t-test there. It just took me a while to find it there. This one I think is probably a little bit easier to follow. Maybe it's just that my eyes are old and the bigger writing's helping me. I don't know. Yeah. And the sample size of at least 10. So you want to make sure in your sample you've got at least 10. If you don't, you might need to comment on why you still think it's appropriate, or you may need to look at using another test. Probably for most of you, you can justify that you're expecting it to be normally distributed and be able to go on with this. But in the current climate, I don't know how you've collected your data, maybe or maybe not. So what do? We compare the sets of data and measure the amount of overlap between the two sets. So how much do they overlap? How similar are they? And thereby, by measuring how similar they are, we also get an indication of how different they are. Only two-tailed paired and unpaired tests are expected. So what do they mean by two-tailed? So when you're doing a t-test, with your null hypothesis, your null hypothesis, usually there's no difference between these two groups. There won't be any difference observed. Your H1 hypothesis, your research hypothesis may be that what they're saying there, if they want it to be two-tailed, your research hypothesis should be there will be a difference. It doesn't need to say that condition B will be significantly better than the regular condition. That would be a one-tailed test because you are specifying beforehand in what direction you think it's going to happen. You don't know necessarily what direction your whatever your intervention is, whatever it is you're changing, the variable that you're changing, you're not sure what impact it's going to have. You may have a suspicion that it's going to affect it in a particular direction, but you can't be sure unless you're replicating someone else's experiment or an experiment that's been done a number of times. You can't really be sure whether your intervention is going to make it a better performance or a worse performance overall. What you're trying to show is that it's that it will have an effect, positive or negative. So that's why it's a two-tailed test. Paired and unpaired just depends on whether or not you've got the same people working in two conditions or you've got two different groups. And again, you can look at that. While students are not expected to calculate a value for the t-test, can be shown how to calculate such values using a spreadsheet program or the graphics display calculator. And there's a place where you can go that will probably take you through that fairly easily. The scientific community defines an objective standard by which claims about data can be made. That's a talk link there. So that's just talking about why is it that we use an alpha of 5 or 0.05 or an alpha of 0.1 or 0.01. It really depends on the situation. How certain do you need to be that you're not making an error and saying there's a relationship when there isn't? Probably with sports, you don't need to be so precise. If it was a drug with massive side effects, you might want to be pretty sure you're right. So that's when we might use an alpha of 0.01 or something like that. Alpha being the possibility that I'm rejecting a null hypothesis that is actually true. Explain that the existence of a correlation is not a causation. We've talked about that. While calculations of these values are not expected, students who want to use R and R squared in their practical work, yes you do, could be shown how to determine such values using a spreadsheet program. And again, we've talked about how you can do that on your calculator and up here, how to do it on a spreadsheet. If you're interested, some of you may want to look at another program called Fathom, which is another way of representing statistical data. It's used by a lot of high school students. You'll see it actually mentions it in there as well. It's a free download, at least for a trial, and that would be enough to get you through. But Excel's fine as well. Just sometimes a little bit more tricky to deal with. There are great online sites too that if you just go like ttest online and look it up, that will be able to help you. Sorry that it's a bit all over the place. It's a bit tougher when you're not in here and I can't ask you questions, you can't ask me questions, vice versa. But that should give you an idea about what you're going to need to do, what sorts of things are going to be important. I really would stress, 1, get the little things right. Label your diagrams correctly, do all of that. Justify the decisions you're making. So you're probably going to use a t-test. Make sure you're justifying those things as they say here. Data should be normally distributed and a sample size of at least 10. Justify that you've got that. When you're making a decision about which test to use, maybe talk through one of these flowcharts. It's not a bad idea to have. You probably know where you're going to end up here, but still talk through the process. If you end up with a Wilcoxon because you're happy to say that you're not confident that it's normally distributed data, that's okay. You are able to do that as well. Remember that you need to do a two-tailed test so that you're not specifying in your alternate hypothesis in which direction it's going. You're just saying that it will be different, that it will have had an impact in some way. That should be enough to get you started. Sorry for jumping around a little bit, but hopefully that helps. I'm happy to catch up with you guys now when you're back at school, possibly, or in a Zoom session, and we'll talk some more. Good luck with everything, guys. Keep up your great work. Cheers.